Okay, we'll get started. Good morning. I hope y'all have been having a good week so far. And yeah, hopefully everything's been going good for you so far. Hopefully you do realize we have basically like 2.5 weeks of school left, especially if you're a senior. You know, that last finals week is essentially like your checkout week. Hopefully all your classes are finished up before that final week. And so that also means we are basically 2 weeks out exactly from the AP exam. All right, so if you're planning on taking that exam, hopefully you have already gone through the steps of making sure the testing app is downloaded on your computer and that it works and that you've logged in. If you previously registered to take the AP exam, but you are not planning on taking the exam, please don't just not show up. That won't work out in your favor. All right, cancel the exam if you're not planning on taking it. You have up until 8 days prior to the exam date. So if you wait till this time next week and decide you want to cancel, you're too late to cancel your exam if that's something you want to do. Otherwise, keep doing what you're doing. Last time I checked, there are still some people in this class that have not signed into the testing app. This really should be done soon. All right, it's going to be easier to make sure everything works now than to wait till you're trying to get your testing stuff ready. All right, some of you might have other exams that are starting before the AP Stats exam, right? And you need to make sure this thing is all up and running. So that's my little spiel again. Please, if you have not and you're planning on taking the exam, make sure you do all those things. Also, when we get to that 3-day out mark, that's when you can do your like exam setup. It's that first section of like registration, I guess, for the exam that you can do on the app demo or the practice exam under practice. And then remember that day of the exam, you have your last little part of, you know, signing into the exam, so to say. All these things happen easier if you've already made sure the app works. So please do that. And if you need help, let me know, or contact someone at your school site who knows how, something. Get the help you need. All right, so there's that. Also, looking forward for us. This week, you know, today and tomorrow, we'll be covering Chapter 3. I don't have an activity necessarily for Chapter 3. I want to make sure that we kind of see the content and understand some of it. Right? We're definitely not going to be experts at Chapter 3, but we're going to see it so that it's at least something that we're aware of. And so today we're going to do all of Section 3.1, which is a fairly short presentation. And then part of Section 3.2, we'll finish 3.2 tomorrow, and then see some examples of how these things show up on AP exams. We'll look at a couple of previous AP exams that deal with scatterplots, correlation, and least squares regression lines, which is the topic of Chapter 3. So we'll do that. We will be skipping Chapter 12 as a class. I will have resources for Chapter 12 available in Canvas, but rather than spending the last week before the exam trying to cram Chapter 12 in, I want to be able to do some preparation for the exam by doing some previous response questions and some practice. And that's what was recommended to me by people who've taught the course in the past, is that I'm better off skipping Chapter 12 and doing Chapter 3 and then doing practice. So that is what we're going to do. And at the end of the day, the content from Chapter 12 represents about 2 to 5% of the possible questions on the exam. So it's a gamble to basically say like, well, we're just not going to cover that and hope for the best. It's the best we can do in the situation we're in. So there's that. Also, keep in mind, because of the way the scheduling is, the last time I will see you is on test day. unless you're testing for something else that day, right? Otherwise, we're only going to see each other next week, Thursday, Friday next week, and then it's AP exam the following Thursday. Get the most out of our time that we have. So it's a little unfortunate thing with the way they did the scheduling for this semester. So there's that as well. So I want to make sure that we're aware of that. Lastly, as far as this class is concerned, I will not have a formal final. You're responsible to just try and complete the things that have already been assigned in the course. There will only be one more multiple choice assessment assigned, and that will be covering chapter 11 and chapter 3. Most likely it's just going to be 15 questions rather than just 10 because it is covering 2 chapters. But there will not be a free response question assessment for this last 2 chapters. Right, so there will just be one more multiple choice assessment. It should be assigned by tomorrow, and you'll have through the end of the semester to complete that. Yes, and that's it. Are there any questions about how we're wrapping up the semester?
What is the last day to turn in late assignments? Just curious.
Well, if you're a senior, I need to have your grades in before graduation. So best would be the 11th. If you're not a senior, I have a little bit extra time to get your grades in. I have basically till the end of, I think like the 17th or 18th. I have to check with the person who does, who's in charge of grades for the district, but I believe that's the timeline. Does that answer your question? Perhaps. I'm going to go with that your question was answered. Are there any other questions? All right, so then we're gonna go through our lessons for today. We're starting with chapter 3, which is describing relationships. And this is among quantitative data. If you remember, chapter 11 was dealing with categorical data. And this section is kind of akin to that. Go away, little presentation thing, okay. Cool. So here we go. Section 3.1 is scatterplots and correlation. You may or may not have seen scatterplots in the past. You might have seen them in Math 1, possibly again in Math 2, in our stats sections. Maybe not. So here we go. In this section, we're going to learn how to identify explanatory and responsive variables in situations where one variable helps to explain or influences the other. Make a scatterplot to display the relationship between 2 quantitative variables. Primarily, we want to know how to do this in our calculator, because remember on the AP exam, since we're doing the digital version, you will not be expected to draw a scatterplot or any type of graph, but you might need to have it produced on your calculator so you know what it looks like. Describe the direction, form, and strength of a relationship displayed in a scatterplot and identify outliers in a scatterplot. Interpret the correlation. Understand the basic properties of correlation, including how the correlation is influenced by outliers. Use technology to calculate correlation and explain why association does not imply causation. So first, explanatory and response variables. Most statistical studies examine data on more than one variable. In many of these settings, the 2 variables play different roles. A response variable measures an outcome of a study. An explanatory variable may help explain or influence changes in a response variable. So the big thing is the response variable is the thing that you're actually collecting data on. The explanatory variable is something else that can explain it. Wrong button. Note, in many studies, the goal is to show that changes in one or more explanatory variable actually cause changes in a response variable. However, other explanatory response relationships don't involve direct causation. There may be two things that have an association, but one is not necessarily causing the other. We'll talk about that later. Does anyone need a moment to write any of this down? A scatter plot shows the relationship between two quantitative variables measured on the same individuals. The values of one variable appear on the horizontal axis and the values of the other variable appear on the vertical axis. Each individual in the data appears as a point on the graph. So this is similar to a dot plot, except this dot plot has an X and Y axis rather than just a horizontal axis. To make a scatter plot, you first need to decide which variable should go on each axis, knowing that the explanatory variable goes on the x-axis. So really, once you identify which is the explanatory and which is the response, you know which variable goes on which axis. There is a reason for this. It's more apparent in section 3.2. You need to label and scale your axes. All right, once you've drawn them, if you're drawing them by hand, you need to label them properly and then scale the axes. When they say scale, that means that you need to use a common spacing for your axes, meaning don't just use values that show up in your data. It's not appropriate to label like the hash marks on your x-axis as 1, 3, 7, 10, and 25 because those are the only numbers that show up. You need to go by a common increment, 5, 10, 15, 20, 25, 30, right? The spacing needs to be consistent. You do not need to use the same spacing for the X and the Y axis, but you need to be consistent for X and then consistent in the scale for Y. Lastly, plot individual data values. Once you have your X and Y axis set up, you can plot your points. Essentially, it plots the same as coordinates on a coordinate plane. So you need a moment to write anything down from this slide. To describe a scatter plot, follow the basic strategy of data analysis from chapters 1 and 2. Look for patterns and important departures from those patterns. As in any graph of data, look for the overall pattern and for striking departures from that pattern. You can describe the overall pattern of a scatter plot by the direction, form, and strength of the relationship. An important kind of departure is an outlier. Hopefully we know what those are by now. An individual value that falls outside the overall pattern of the relationship. So we need a moment to write anything down. Okay. Two variables have a positive association when above average values of one tend to accompany above average values of the other, and when below average values also tend to occur together. Essentially, as X increases, Y increases. Right, two variables have a negative association when above average values of one tend to accompany below average values of the other. In other words, it's a negative association if as X increases, Y decreases. Think of this as having a positive or negative slope. So here we have an example scatter plot right here. This is our percent taking SAT among, I believe this is among the 50 states. And then we have a mean math score on the SAT. This is the percentage of students taking the SAT. We're going to describe the scatter plot. So there is a moderately strong negative curved relationship between the percent of students in a state who take the SAT and the mean SAT math score. Further, there are two distinct clusters of states and two possible outliers that fall outside the overall pattern. Right, and so again, we see a negative association because as x increases, y is decreasing. It is moderately strong because a lot of the points are clustered closely together, meaning on the curve that models this relationship, the points are close to that curve, making it strong. Then we have possible outliers falling outside the overall pattern. And again, we have strength, direction, and form. The strength is moderately strong. Direction is negative. We have a negative association. And curved would be a curved line would model this relationship. And so when we describe a scatter plot, we need to have those three things: strength, direction, and form. And we need a moment to write anything down from this screen. So we have another example, and this comes from an example in the textbook about the SEC football conference relating points per game to wins. So we have direction. In general, it appears that teams that score more points per game have more wins, and teams that score fewer points per game have fewer wins. We say that there is a positive association between points per game and wins, because as points per game increases, so do the wins. So we have a positive association. Form. There seems to be a linear pattern in the graph. That is, the overall pattern follows a straight line. Okay, this does not appear curved like our previous example. This just seems like we can model it with a straight line. Lastly, strength. Because the points do not vary much from the linear pattern, the relationship is fairly strong. There do not appear to be any values that depart from the linear pattern, so there are no outliers. If we drew a best fit line, a lot of these points would be relatively close to that line. Right. The scatter plot displays the strength, direction, and form of the relationship between two quantitative variables. Linear relationships are important because a straight line is a simple pattern that is quite common. Unfortunately, our eyes are not good judges of how strong a linear relationship is. The correlation R, so we have a new statistical variable here, R, measures the direction and strength of the linear relationship between two quantitative variables. R is always a number between -1 and 1. When R is positive, this indicates a positive association. When R is negative, this indicates a negative association. Values of R near 0 indicate a very weak linear relationship. The strength of the linear relationship increases as R moves away from 0 towards -1 or 1. So if it's -1, that's a very strong negative association. If it's +1, it's a very strong positive association. The extreme values R equals -1 and R equals 1 occur only in the case of a perfect linear relationship, meaning all of the points lie exactly on a straight line, which is really never going to be the case. So we need a moment to write this down. So we have some examples with the accompanying correlation R value. Right? In this first graph, we're given a correlation R equals 0, which essentially is a straight horizontal line through the middle here. It's not negative, it's not positive, it's just a big clump of points. Right, we have a correlation R equals negative 0.3. If we look at this, there is a slight negative association. As we increase on X, the Y values tend to decrease a little bit. It's not super crazy, but there is a slight negative turn. Correlation to 0.5. Right, now we have a slightly more positive association. Negative 0.07, more negative. 0.9, nice strong positive association. Negative 0.99, almost a perfect straight line here. Right, so it's just a few examples of how R relates to how clustered or not clustered, how closely the points look like a line, or can be modeled with a line. Is there anything I can clarify here? So now we want to be able to calculate the correlation. The formula for R is a bit complex. It helps us to see what correlation is, but in practice, you should use your calculator or software to find R. Use your calculator, because this formula sucks. Suppose that we have data on variables X and Y for n individuals. The values for the first individual are X1 and Y1. Values for the second individual are X2 and Y2, and so on. The means and standard deviations of the two variables are X bar and S sub X for the X values and Y bar and S sub Y for the Y values. The correlation R between X and Y is this hot mess of a formula. We have R equals 1 over n minus 1 times the sum of the products of the difference of each point minus the mean for the X values divided by the standard deviation of the X value times each Y value minus the mean of the Y values divided by the standard deviation of the Y values. Essentially, this is the product of the standardization of each point summed up. Yeah. It's a mess. You don't want to do this by hand. We have the shorthand version here using our sigma notation for summation notation. We want to do this on our calculator. Okay. We really don't want to do this by hand. If you are asked to do it by hand, chances are it's only like 4 data points for each list. It'd be really short, otherwise it'd be really mean to do. So in your calculator, let's make this a little bigger. Right, in your calculator, you will want to go to Stat, Edit, and I already have data in my lists here. This data set goes along with the scatterplot example that we saw earlier with points per game and wins. Right, my L1 list is the points per game. L2 is wins. Right, so I've got the data for all of our teams in the SEC here and the number of wins that they had. Right, they had 12 teams, right? And we have that. So you put L1 should be your explanatory variable, your X variable. L2 is the response variable or the Y variable. Okay, once you have this in there, we can then go back to stat. We'll calculate, and what we'll actually use, which we'll need it for section 3.2, but what we'll use here is this linear regression A plus BX. Notice there's another linear regression, AX plus B. That's for a different type of modeling. We want this one, A plus BX. There's even another one, I believe. That's just linear regression. We don't want to use that one. We want the 8th option here. Your calculator will default to use L1 as the X list and L2 as the Y list. So that's good. Already set up. We don't need to worry about the frequency list. We want to store the regression equation so we can use it again later if we need to, which we will. All right, and to do that, we'll go to vars, yvars, function. Where'd my mouse go? Lost my mouse. There it is. And then just select y1. It will store the equation that it comes up with in y1 in our graph y equals. You know, if we hit this button, we'll see it. So we'll store it there, it pops that in there, and then we'll calculate. Boom. It gives me y equals a plus bx. I have my a value, my b value. We'll talk about what those represent later. We have r squared, which again we don't need yet. But here's r. We want that one. That's my correlation. Right? R is 0.9358, blah blah blah, meaning we have a very strong positive association. Right? This shows a very strong association. Now, here's the other thing. Your graphing calculator might not be set up to show r squared and r when you do this regression. Right? You need to fix that if it does not. You need to go to mode and make sure your calculator's got a setting on it. Right? We want the stat diagnostic setting turned on. Right? Stat diagnostic needs to be turned on. It defaults to off. When it's off, your calculator will not give you r squared and r when you run the linear regression. When it's on, it will. We want it on. Okay? So make sure it's turned on. Is there any questions? Here's my regression equation. And there's my graph. Shows my scatter plot and my regression line. And the trick, if you're not sure what size window to use, you want to use the zoom stat window. Just go to zoom and go zoom stat, and it'll make it fit your data. All right. Any questions? All right. So again, we're going to want to be familiar with how to use the calculator to do this, because again, you're not going to be asked to draw the scatter plot, right? But you might need to refer to it, and you're going to want those values. Facts about correlation. How correlation behaves is more important than the details of the formula. Here are some important facts about R. Correlation makes no distinction between explanatory and response variables. In other words, if you make a mistake and put your explanatory variable on the y-axis and your response variable on the x-axis, you'll get the same R score regardless. You'll get the same R value. Same thing with R squared, which we'll talk about later. R does not change when we change the units of measurement of X, Y, or both. Meaning if we transform our units, like if we standardize all the values in X and standardize all the values in Y, R won't change. Correlation R itself has no unit of measurement. It's just a value. Cautions. Correlation requires that both variables be quantitative. Correlation does not describe curved relationships between variables, no matter how strong the relationship is. So again, we should only be using the correlation value R when we have something that we can model with a line. Right? If it looks curved, this is not a good model. We do not want to use correlation. Correlation is not resistant. R is strongly affected by a few outlying observations. This is primarily because R is calculated using mean and standard deviation. Mean and standard deviation themselves are not resistant to outliers. So R is not resistant to outliers. Correlation is not a complete summary of two variable data. It's just one measure and one value. All right. So you need a moment to write anything down. All right. Excellent. I think. So here we go. That's the end of the presentation for this section. The only thing that I want to pause on here is explaining why association does not imply causation. Right? We can find an association between a number of different variables. It does not mean that one is causing the other. Okay, an example of this that I like is popsicle sales versus shark attacks. Right? Typically, we'll see higher popsicle sales when there's higher shark attacks. This is primarily due to the fact that popsicles sell more during the summer where more people are at the beach and there's more people at risk of shark attacks. The popsicle sales are not causing the shark attacks, but there is an association. So just because there's an association between two variables does not mean that one causes the other. Right. So anything I can clarify? Right. So we will stop this presentation and move right on into 3.2. Yeah. No. Yes. There we go. Go away a little bit. There we go. All right. Sorry about that. So here we go. Section 3.2. This is least squares regression. So in this section, we want to learn how to interpret the slope and y-intercept of a least squares regression line. Use the least squares regression line to predict y for a given x. Calculate and interpret residuals and their standard deviation. Explain the concept of least squares. Determine the equation of a least squares regression line using a variety of methods, primarily using our calculator. Construct and interpret residual plots to assess whether a linear model is appropriate. Assess how well the least squares regression line models the relationship between two variables, and describe how the slope, y-intercept, standard deviation of the residuals in R-squared are influenced by outliers. So first, regression line. Hopefully, in previous math classes, you've seen regression done before. Making regression lines, we can do quadratic regressions, cubic regressions. In this case, we're only concerned about linear regressions. Right? A linear straight line relationship between two quantitative variables are common and easy to understand. A regression line summarizes the relationship between two variables, but only in settings where one of the variables helps explain or predict the other. A regression line is a line that describes how a response variable y changes as an explanatory variable x changes. Right? We often use a regression line to predict the value of y for a given value of x. And they have an example here showing miles driven versus price. This is having to do with a used car. More miles it's driven, the less value it has. A regression line is a model for the data, much like density curves. The equation of a regression line gives a compact mathematical description of what this model tells us about the relationship between the response variable y and the explanatory variable x. Right, suppose that y is a response variable plotted on the vertical axis, and x is an explanatory variable plotted on the horizontal axis. And this is why in the previous PowerPoint, we saw that the explanatory variable goes on the x-axis and response goes on y. It's to make this regression line thing do what it's supposed to. A regression line relating y to x has an equation of the form y hat equals a plus bx. And this is why we chose that a plus bx regression on the calculator. In this equation, y hat is the predicted value of the response variable y for a given value of the explanatory variable x. It's kind of like the expected value, the predicted value. B is the slope, the amount by which y is predicted to change when x increases by 1 unit. A is the y-intercept, the predicted value of y when x equals 0. Right, so the parts of this essentially is what we expect it to be just from the equation of a line that we hopefully all know. And all the parts behave just the same way as a regular linear equation would. So we need a moment to write anything down. Right, so here we have our same scatter plot with regression line here from miles driven versus price. We have price hat equals 38,257 minus 0.1629 times miles driven. We want to identify the slope and y-intercept of the regression line and interpret each value in context. Interpret in context is something you need to get very used to. This is asked often. Solution. The slope b equals negative 0.1629. Tells us that the price of a used Ford F-150 is predicted to go down by $0.1629 or 16.29 cents for each additional mile that the truck has been driven. And again, that makes sense considering what we know about linear equations and linear functions. The y-intercept, A equals 38,257, is the predicted price of a Ford F-150 at 0 miles. Again, this translates exactly the way that we would expect a linear function to translate. Continuing on with the same example here, we can use a regression line to predict the response y hat for a specific value of the explanatory variable x. We can use a regression line to predict price for Ford F-150 with 100,000 miles driven. Right? We have that, should be around 22,000. We have a price hat equals 38,257 minus 0.1629 times miles driven. We substitute in the 100,000 for the miles driven. And we get a price, a predicted price of $21,900. I can't read today. $21,967. Again, so that works the same way as any linear equation would work. We can use a regression line to predict the response y hat for a specific value of the explanatory variable x. The accuracy of the prediction depends on how much the data scatter about the line. Right, so essentially, the stronger the association, the closer r is to -1 or +1, the more accurate the prediction is. Because remember that r value tells us how close the points are to the linear model. The farther away they are, the less accurate our prediction is. While we can substitute any value of x into the equation of the regression line, we must exercise caution when making predictions outside the observed values of x. So whenever using values that are outside the range of values of x, right, that are in our data set, you're taking a little bit of a risk. Right, extrapolation is the use of a regression line for prediction far outside the interval of values of the explanatory variable x used to obtain the line. Such predictions are often not accurate. Don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. That's just the caution. Don't go way outside your data set. That brings us to residuals. In most cases, no line will pass exactly through all the points in a scatter plot. A good regression line makes the vertical distances of the points from the line as small as possible. So again, we're talking about vertical distances, which is tracking how far away each point is from the regression line on the y-axis, essentially. The residual is the difference between an observed value of the response variable and the value predicted by the regression line. And so we have our miles driven and price, and we have these little lines here that connect each point back to the regression line, right? Showing the vertical deviation. That is the residual. Our residual is equal to the observed y minus the predicted y. So we have y minus y hat. Right? These can be positive or negative. Right? Points that are below the line, those get negative residuals. Above the line, positive residuals. Would anyone like a moment to write this down? Different regression lines produce different residuals. The regression line we want is the one that minimizes the sum of the squared residuals. The least squares regression line of y on x is the line that makes the sum of the squared residuals as small as possible. Right. And that is why we're using that specific linear regression command in the calculator, because it's for this least squares regression. Right. And so then we got a couple of graphics here showing miles driven versus price, a squared residual, and then the sum of the squared residuals. Bleh. One of the first principles of data analysis is to look for an overall pattern and for striking departures from the pattern. A regression line describes the overall pattern of a linear relationship between two variables. We see departures from this pattern by looking at the residuals. A residual plot is a scatter plot of the residuals against the explanatory variable. Residual plots help us assess how well a regression line fits the data. So again, here we have the same scatter plot and regression line that we've been seeing with miles driven versus price. And here we have the residual plot. Right. This shows this zero line across the middle here represents the regression line. These points are showing the distance, vertical distance, positive or negative, between each point and the regression line. Right, so it allows us to see if there's any crazy departures. A residual plot magnifies the deviations of the points from the line, making it easier to see unusual observations and patterns. The residual plot should show no obvious patterns. The residuals should be relatively small in size, meaning compared to the rest of the residuals. If we were to have a residual plot looking like this, where there is an obvious pattern, it looks like a parabola. Right. And this is the actual x versus y plot. This is obviously a curved scatter plot. The linear model is not appropriate. Right. We have an obvious pattern. If you see an obvious pattern in the residuals, a linear model is not okay. We don't want to use it. To assess how well the line fits all the data, we need to consider the residuals for each observation, not just one. Using these residuals, we can estimate the typical prediction error when using the least squares regression line. Right. Remember when we're trying to find the typical variance or the typical deviation from what we expect to happen. That's standard deviation. If we use a least squares regression line to predict the values of a response variable y from an explanatory variable x, the standard deviation of the residuals, s, is given by this horrible formula. S equals the square root of the sum of the residuals squared divided by n minus 2. We have n minus 2 here because we have 2 data sets. Pardon me. And in nicer notation here, the square root of the sum of yi minus y hat squared divided by n minus 2. This value gives the approximate size of a typical prediction error residual. Okay, this should look familiar because under the square root here is essentially a modified version of the variance formula that we've seen a while ago. And remember, this standard deviation is the square root of the variance. And so there's that. Again, your calculator will find this for you. We do not need you to do this by hand, especially if you've already used the data. I'll show you this in just a moment. And then we also have what's called the coefficient of determination. The standard deviation of the residuals gives us a numerical estimate of the average size of our prediction errors. There is another numerical quantity that tells us how well the least squares regression line predicts values of the response y. The coefficient of determination, r squared, is the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. We can calculate r squared using the following formula. R squared equals 1 minus the sum of the residual squared divided by the sum of yi minus y bar squared. Or you can square the correlation r. It gets the same number. R squared tells us how much better the least squares regression line does at predicting values of y than simply guessing the mean y for each value in the data set, right? And it's essentially a proportion, it's a percentage. R squared ends up being a kind of a probability, and it tells us how well our least squares regression line accounts for and predicts values of y based on x. Right. So, and that's why r and r squared are very closely related. It's based on the correlation. Yeah. So here we go back to the points per game and wins example. Right, we looked at the relationship between the average number of points scored per game, x, and the number of wins, y, for the 12 college football teams in the SEC. Scatter plot with the least squares regression line and residual plot are shown. The equation of the least squares regression line is y hat equals negative 3.75 plus 0.437x. Also, s is 1.24 and r squared is 0.88. We have our scatter plot and residual plot. Now, if we look back at what we've done in the calculator here, we already saw we can calculate the regression line, the equation of the regression line, and that's what we have here. When we did that calculation, we got A, we got B, right? We have the intercept and the slope, and we also got R and R squared, but we didn't get S, right? And we do not want to calculate S by hand, right? To get S, we need to do a different function on the calculator, right? And we need to do a distribution calculation. Oh no, wait, I'm sorry, wrong thing. I don't want that anymore. Yeah, that should be okay. We go to stat and we go to tests. Right? We want a test that's down here. The linear regression t-test. This is going to give us the values we want. It's going to give us a lot of other things that we don't need right now, but it'll give us what we want. Again, we'll use the same list. that we already had in the calculator because they had this based on our points per game and wins. Right? Frequency, we don't need to worry about that. We don't need to worry about this beta and phi thing right here. That has to do with doing an actual significance test, which we're not going to look at. I showed this previously, so we already have the regression equation as y1 because that's where I stored it originally. Right, so I'm having it refer back to that regression equation because it needs that to do the calculation. We would populate this the same way that we did previously. Right, we're going to go to vars, y vars, function, and then hit enter on y1 because that's where it's stored. Click calculate. Where's my mouse? I lost my mouse again. Where'd you go? There it is. All right, we get a whole bunch of stuff. All right, again, we have this T and P, right, in degrees of freedom, which goes along with stuff we would expect for a significance test. We also get the intercept, negative 3.75. That matches what we have on our slide there. B, 0.437. That's good. But we get S. Yay, there's S, 1.235, blah, 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 blah. They've rounded it to 1.24. We get R squared, right, 0.87, blah, blah, blah. And we also get R. Right, so running this gets us a little bit more information. However, we need to run that linear regression first for this to work properly because it's referring to that equation, I believe. At least that's how I've done it, and it works this way, so I get the right values. Any questions? Cool. All right, so here we have these things. So we want to calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. Predicted amount of wins for South Carolina would be 9.4 wins based on our regression equation. The residual for South Carolina would be y minus y hat, which is 11 minus the expected wins, 9.4, and we get 1.6. South Carolina won 1.6 more games than expected based on the number of points they scored per game. Yeah, they did better than expected. We want to know, is the linear model appropriate for these data? Explain. Here we have our residual plot for reference. Because there's no obvious pattern left over in the residual plot, right? We don't see an obvious curve or anything like that. The linear model is appropriate. There's also nothing like, compared to all the residuals, there's no like crazy large or crazy small point. We want to interpret the value S equals 1.24. When using the least squares regression line with X equaling points per game and to predict Y, the number of wins, we will typically be off by about 1.24 wins. Right, that's essentially the standard deviation. And we want to interpret the value R squared equals 0.88. This means about 88% of the variation in wins is accounted for by the linear model relating wins to points per game. Right, so that's what R squared represents, basically how accurate our linear model is. Right? Is there anything I can clarify? All right, we're going to stop here. Today we'll pick up tomorrow the rest of it. So if there are any questions, comments, concerns, anything you need help with, please make sure you let me know so I can help you. Other than that, we'll continue tomorrow with the rest of chapter 3. We'll get some examples in. I'll go over some examples based on previous AP exams on where these things show up. And that'll be it for the week. So I hope you have a great rest of your day, and we'll see you all tomorrow.